Good morning, students. Our new chapter, electromagnetic induction. What is electromagnetic induction? Means electric current is generated in a closed coil. So like this, if suppose it is a closed coil. So due to change of magnetic flux through this coil, so you have to pass the magnetic lines of force, if suppose. So when the magnetic lines of force or magnetic flux through this coil will be changes, so induce of electric current. This phenomena is called as the electromagnetic induction. If suppose this coil, a circular coil ends will be connected to a galvanometer, so when the magnetic flux through this coil will be changes, you have to observe the deflection. So this phenomena is called as the electromagnetic induction. So for this, experiments of Faraday and Henry. So first experiment. So in that first experiment, we will take the one circular coil. This circular coil is connected to a galvanometer. So it is a bar magnet. So the bar magnet, the magnetic lines of force started at the north pole and they will be ended at south pole. So when this bar magnet north pole is pushing towards, so at that time there is a change of magnetic flux you have to observe in the coil C1. So when the magnetic flux through this coil will be changes, so automatically there is an induce of EMF. So this phenomena is called as the electromagnetic induction. So how to notice this one? By connecting galvanometer. So this circular coil is connected to a galvanometer. So G. So when the north pole is approaches to the coil, automatically it show the deflection maybe like this. If it is a deflection like this, it is pushing towards north pole. If suppose north pole is pushing outwards in direction, automatically in previously it is the direction means if suppose it is the direction deflected. So when a north pole is withdrawn from the coil, it show the deflection like this in opposite manner. So similarly, you have to change the polarities. You have to take the south pole now. So when the south pole is approaches, so what is the deflections you have to observe in the point of north? So you get the deflections in opposite manner. So when the north pole of this bar magnet is approaches or away, so at that time means or otherwise you have to take this coil is approaching or this coil is moving away. At that time also you are getting the deflections. So at that time also you are getting the induce of EMF in the coil. So when these two are moving with the same velocity, if suppose these two are moving with the same velocity means there is no change of magnetic flux. There is no change of magnetic flux through this coil. So at that time there is no deflections. There is no deflection you have to observe from the galvanometer. So what you have to conclude finally, you have to change the magnetic flux through this coil. At that time only you get the deflection. So finally the point is the relative motion between the magnet and the coil that is responsible for generation of electric current in the coil. So for this experiment, so you have to take the bar magnet. This bar magnet is pushing towards or moving outwards direction along the axial line. At that time you have to observe the deflections in the galvanometer. So if suppose pushing towards, what is the direction you have to observe? So in opposite directions in the case of withdrawn from the coil. So it is the experiment 1. And next experiment is, if suppose previously what you have to take in the coil C1, and in the place of bar magnet now you have to take a circular coil C2. So this circular coil is replaced by a bar magnet. It is nothing but a solenoid here. So if suppose if it is the soft iron rod, this is wounded by a conducting wire. So that conducting wire ends will be connected to a battery. At that time this soft iron rod will behave like as a bar magnet. So already you learned in previous chapter this is. So what I am taking, it is also a bar magnet. It is also a bar magnet. So these two ends of circular coil will be connected to now here battery. So this coil C2 is now connected to a battery, but this coil C1 is connected to a galvanometer. So when this will be connected to a battery means here the current will be flowing. So when here the current will be flowing like this. So at that time there is a induce of magnetic field along the axial line. So automatically the magnetic field will be increases or decreases depending upon this battery. You have to high power you have to apply here, automatically the magnetic flux will be greater. So less power you have to apply, less. So automatically this coil now behaves like as a bar magnet. So this will be you have to pushing towards, automatically there is a change of magnetic flux through this coil. At that time this galvanometer shows the deflection. So it is pushing outwards, automatically what is the deflection you have to observe in previous, in opposite direction you get the deflection. So this coil C2 now act as a bar magnet. So in previously what is the bar magnet is pushing towards. Similarly this coil C2 you have to pushing towards or outwards. At that time you get the deflections in the galvanometer. That means there is an induce of electro EMF. There is an induce of EMF in this coil that will be noticed by this galvanometer. So if suppose these two are moving with the same velocity in same direction, so if suppose these two are moving like this, these two are moving in same direction, at that time there is no deflection. Why? Because at the case of only change of magnetic flux through this coil, you get the deflections. If suppose there is no change of magnetic flux through this coil, there is no deflections. So in third case, if suppose these two coils are at a stationary, these two coils at a stationary, so one coil is connected to galvanometer, one coil is connected to battery, but through tap key. If suppose this tap key will be open means the circuit is in open. So when the circuit will be closed, at that time this coil will be closed circuit. When the tap key is pressed means automatically current will be flowing through this coil. There is a magnetic flux will be created along the axial line. So automatically previously there is no magnetic flux. So when the tap key you have to press, the magnetic flux will be created and that will be passing through this axial line. Automatically you get the deflection, a momentary deflection like this. If it is shown like this. Why? Because you have to continuously press it. At the time of continuously pressing, the magnetic flux, so if suppose 20 number of magnetic lines will be passing through this coil, so the number will not be changed. You have to press it continuously. If suppose pressed and released, automatically you get the deflection like this. So the number of magnetic lines first of all increases like this, deflection. When the you have to get continuously pressed means a constant number of magnetic lines of force will be passing. Only in case of relative motion, so it is pushing towards, at that time also you get the deflection, but will not be changed. You are not changing the number of magnetic lines of force. At that time there is no deflection you have to observe. So from these three experiments, what you have to conclude that means, from first experiment you have to pushing towards, at that time change of magnetic flux. So in second case, so you have to, the bar magnet is replaced by a circular coil C2. At that time also you are getting the deflections, but here you have to insert a tap key. So you have to press it means a momentary deflection. Momentary deflections. You have to press it means it gets a deflection and come back. Why? Because a constant number of, you are to pressing continuously means a constant number of magnetic lines of force will be passing. If suppose pressed and released means it gets the momentary deflection. Okay. So finally what you have to conclude, you have to change the magnetic flux through the coil. At that time there is an induce of current or EMF that will be noticed by galvanometer. And next topic is the magnetic flux. Already you have the topic in previous chapter. So what is the magnetic flux means? the total number of magnetic lines of force passing normally through any surface area is called magnetic flux. So what is the magnetic flux means? If suppose it is a magnetic flux, so this magnetic flux will be passing through any unit area. If suppose it is the plane, this is the plane you have to take. So what is the this area vector will be like perpendicular for this plane. If suppose this will be like this, so if suppose like this, it is our palm. So at the time the direction will be like this. So for this case, if suppose the magnetic lines of force will be passing along this direction, from it is the direction of magnetic lines of force will be coming. So this is the plane you have to take in. So what is the magnetic lines of force will be passing through this will be the total magnetic lines of force. If suppose it is a plane means there is no magnetic lines of force will be passing through this unit area. So at the time only the maximum number of magnetic lines of force. So at the time the area vector and the magnetic lines of force both will be parallel. So parallel means 0. So at the time, so at the angle 0 will be, at the time of angle 0 it will be maximum means cos 0 will be maximum. So the dot product of B dot A means here, so BA will be maximum at theta is equal to 0 degrees. So and theta is equal to 90 means at the time there is no magnetic flux will not passing through that area. So the total number of magnetic lines of force passing normally through any surface area is called as the magnetic flux. So its units is equal to Weber or Tesla meter square. Okay, next Faraday's law of induction. So what are the experiments you have to done in by Faraday and Henry? So first experiment, in the case of first experiment, coil C1 and bar magnet. You have to bar magnet pushing towards or away. At that time there is a change of magnetic flux. There is a change of magnetic flux through the coil and induces the EMF. So based on that, so you have to change of magnetic flux through a closed coil. So induce of EMF. So the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So you have to change the magnetic flux through the coil. So there is an induce of EMF. If it will be changes more means it will be induced EMF will be greater. So these both are in directly proportional. So in case of single turn, it is the formula induced EMF is equal to minus d phi b by dt. The magnitude of the induced EMF. So EMF is induced only there is a change of magnetic flux through the coil, through the circuit, through the circular coil. So induced EMF is equal to minus d phi b by dt. In case of single turn of coil you have to take it. So if suppose that coil having n number of turns, at the time induced EMF is equal to minus n d phi b by dt. So it is the induced EMF, and similar for that induced current is equal to E by R. So by R you have to divide it for that. So I is equal to E by R minus 1 by R d phi b by dt, and in case of n turns minus n by R d phi b by dt. So you have to already you know a right hand thumb rule. So if it is the right hand, so if it is the direction of the magnetic lines of force, it is the direction of the current. But from this diagram, if it is the direction of the magnetic field, but what is the direction of the induced current will be opposite manner. The induced current will be opposite manner. But according to right hand thumb rule, so when the magnetic flux will be, it is the direction, so the current will be induced, it is the direction, but in opposite direction it will be induces. In opposite direction the EMF is induced. So that's why we are taking here negative sign. That's why we are taking negative sign. For why you are taking negative sign means, so this negative sign is taken because of the induced EMF is in opposite direction. So that is given by Lenz's law. So what is the Lenz's law? The direction of induced EMF in a circuit is always opposite to the change of magnetic flux. So the direction of induced EMF in a circuit is always opposite to the change in magnetic flux. So for this experiment, it is the magnetic lines of force. So at that time, what is the direction of the induced EMF? Like this, in this direction. So it is the magnetic lines of force. According to right hand thumb rule, it is the direction, but in opposite direction the EMF is induced. So for that purpose we are taking the negative sign. So if suppose Lenz's law, so if suppose north pole is approaches to the coil, if the north pole is approaches to the coil, so it is the coil you have to take in. So the phase of the coil will be induced EMF direction. It gives the induced EMF direction. But according to the right hand thumb rule, when it is the direction of the magnetic field means, what is the direction in? It is the direction induced the EMF, but in opposite direction the EMF is induced. So the phase of the coil will be like as a N. What is the shape of the phase of the coil will be N. So when the north pole of the magnet is approaches to the coil, the phase of the coil will be, it is the shape, and the induced EMF direction will be in which manner means counterclock direction. In which direction? Counterclock direction. The induced EMF direction is counterclock direction. So when the north pole is approaches towards to the coil means the number of magnetic lines of force passing through this coil will be increases. That means magnetic flux through the coil increases when the north pole is approaches. And it is the north pole, it is the north pole. What is the, which type of force will be acting? A repulsion. So when the north pole is approaches, the phase of the coil will be like as a N. So there is a repulsion. So you are doing a work against of this repulsion. So that work done. So what is the work done? So that work done will be here according to law of conservation of energy. So what is the conservation of energy? The energy neither be created nor be destroyed. So what is the work done? So and the second formula, the energy neither be created nor be destroyed, but it will be converted from one form to another form. So you have to do the work. What is the work you are doing here? The north pole of the bar magnet is pushing towards against of this repulsion. So that work will be create the induce of EMF. So what is the work you are doing here? So that work will be here converted in the form of induce of EMF. So in case of the north pole of the magnet withdrawn from the coil, the north pole of the magnet withdrawn from the coil. So what is the phase of the coil you have to take in? It is the north pole. It is withdrawn from the coil. What is the phase of the coil like will be S manner. So what is the induced EMF direction will be clockwise manner. And it is withdrawn means the number of magnetic lines of force will be decreases. So it is the north pole, it is the south pole. What is the, which type of force acting between these two? Attraction. Which type of force will be acting between these two? Attraction. So against of this attraction you are doing work here. In previously you are doing a work against of repulsion. Now here you are doing the work against of attraction. So that work will be converted in the form of induce of EMF. So Lenz's law is a direct consequence of law of conservation of energy. Law of conservation of energy. So this is our first class. So all of you create one group. My mobile number is 9666 323496. So create a group in WhatsApp and inform me. So, and I will once again repeat the class, complete class. So what is the electromagnetic induction means? Change of magnetic flux through a circular any closed coil. There is a induce of EMF. There is a induce of EMF. So for that purpose we are having the three experiment. One is for one experiment, it is a coil C1 and it is a bar magnet. So this bar magnet you are pushing towards or outwards. At that time you are getting the deflections in the galvanometers. If suppose north pole we are getting the deflections, what are the you have to observe? So the opposite deflections you have to observe in the case of south pole. So this bar magnet is now replaced by a circular coil C2. So this circular coil C2, it is also a bar magnet. It is also a bar magnet. It is a electrical, by using electrical bar magnet now. So so this coil C2 also now you have to move pushing towards or outwards. We are induce the EMF. We are inducing the EMF. And third experiment. If suppose in the case of third experiment, if suppose along this axial line I am inserted one rod. It is a soft iron rod along the axial line. So these soft iron rods are used for to prepare the permanent bar magnets, and these soft iron rods will be easily magnetized. So automatically in the soft iron rod, so already permanent magnetic dipoles will be there, but they will be in zigzag manner. When this will be the magnetic lines force will be passing through this coil along the axial line, automatically it will becomes a magnetic material. It behaves like as a magnetic material. So due to this battery, we are induce of magnetic field along the axial line. So due to that magnetic field, extra magnetic field will be created by inserting a soft iron rod. So all of you once look on first example problem. So in the first example problem, how to increase the more deflection in the galvanometer in coil C2 means, first of all we have to increase the more power, or otherwise you have to insert a soft iron rod. So all of you once read the first example problem. And next one is based on these three experiments we are concluded one formula. What is that formula? The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So induced EMF is equal to minus d phi b by dt. Similarly, which formula, like as a already you are having one formula, dx by dt is nothing but velocity. So if there is a change of position means it is nothing but velocity. If suppose change of magnetic flux through any closed coil, that is responsible for induce of EMF. So induce of EMF is directly proportional to the change of magnetic flux. Change of magnetic flux in case of single turn, in case of n turns. Okay, thank you. Bye.